Hi everybody. Let's get started on Chapter 9. I know it's a little awkward, but we're going to start Chapter 9 with Section 8.7, Vectors. You don't want to see that stuff yet, right? So we're going to talk about vectors. We're not going to go completely into vectors. That's something that you'll get more into further in math, but we need to talk about magnitudes. So we're going to talk about the magnitudes of vectors, and we're going to perform transformations both today and when we get a couple sections from now. So that's why we need to talk about vectors. So first of all, a vector is a quantity that has both a magnitude and a direction. We're going to talk about them in relation to a coordinate plane. So we're going to have x-axis and a y-axis. It is represented by a directed segment. That's a fancy way of saying array. So we're working with array. Remember array back from semester 1, chapter 1. Has an endpoint and goes on into infinity in the other direction. So in this particular example, point A is the endpoint. No, I don't want to say it that way. Point A is the initial or the starting point, and then it goes on to point B. Now here's the thing, it's a little bit different from array because it does end right there at point B, but the arrow on the diagram tells you what direction it's going. So the symbol is, on this one, they called it V. You can see the V on the diagram. V with the little ray symbol above it. Or we could call it vector AB. Notice it doesn't have the full ray. It's got like a half arrow at the top. So vector V or vector AB. Here's the thing. A is the initial point. Initial again means start. B is the end point. The arrow tells the direction. And the direction is important, especially when we talk about component forms and other things. The direction also has to do with angles, and we could be doing some trig with those, but we're not going to get that in depth into vectors. So we'll just start with that. So when I know that A is the initial point, notice also A is the start point on my vector. B is the end point where the arrow goes to. So standard position means the initial point is at the origin. So on the ray that I've got on that example, point C is at the origin. That means that it is in standard form. Notice the arrow to D is going out, and that's where we're going to talk about the end point. A vector can be drawn anywhere on the coordinate plane. So we're going to talk about component form, and component form is easy to figure out when your end point is at the origin. Sorry, your initial point. I keep saying that backwards. Initial point is at the origin. So we've got vector CD. And if we're going to talk about component form, we just change everything up slightly. Our parentheses that we usually put in ordered pairing become brackets, or these pointy brackets. And what we're going to do is we're still going to think in terms of x first and y second, but now we're saying from C to D, how far do you go in the x direction? How far do you go in the y direction? So you're going to look at this pretty quickly and say, all right, for C, I go 1, 2, 3, 4, and then I'm going to go up 2. So the component form for vector CD is 4, 2. So start at C, your initial point, and go to D, your end point. However, we can move that around. Let me do this real quick before I switch the slide. So here's point C going out to point D. Here's the thing about this. When I've got this drawn on here, this is in standard position. However, I could move this over here. That is still the same vector, 4, 2, except it's not in standard position. My initial point is now somewhere else. So it's an identical vector, still with component form 4 too. So that's where we're going with this. So component form. If a vector has its initial point not at the origin, you can still write that vector in component form. So we don't tell, it's not telling where point B or point D is. It's telling how do you get from the initial to the end point. So if it's not at the origin, we would do x2 minus x1 and y2 minus y1, the change in x and the change in y. Notice it is important that you take your end point and subtract the initial. Otherwise, you could land somewhere else on your coordinate plane that is not the appropriate place. So we're going from the tip of the tail, from the tip to the tail of that directed segment or of that vector. So let's do some practice. So write the component form of vector EF. So notice this is not in standard form because if it was in standard form, our point E would be on the origin, which it is not. So I know my two ordered pairs. E is my initial point, and that ordered pair is at 1, 5. F is my end point. That ordered pair is at 7, 4. So in order to do my component form, I'm going to have to do my 7 minus 1 and my 4 minus 5. You probably are going to do this a lot quicker, and you're going to say that the component form for vector EF is 6, negative 1. In other words, if I took this vector and I put it into standard position, that is also vector, I don't know, GH. Vector GH also has component form 6, negative 1. So we're not distinguishing a point, we're just saying how does that vector move from the initial to the end point. Vector addition and subtraction, that's not too tough. It's a lot like distributive property and things like that. So it says if vector H is equal to AB and vector G is equal to CD, then vector H plus vector G, you take your x coordinates and add them together. You take your y coordinates and add those together. Because it says that we're adding. If we were subtracting H minus G, we would take our A minus C and our B minus D. So all the same rules apply. Actually, I've got this right here. I forgot. If we're subtracting, we subtract the x's, we subtract the y's. And scalar multiplication. Someday you might do these with matrices, but this feels a lot like anything else. If vector A is at A sub 1, A sub 2, and K is a positive constant, this is just some random number sitting out there, then if I want to know what K multiplied by vector A is, I just multiply K by all the coordinates. So I could have said vector B is equal to 4, negative 2. So if I want to know twice vector B, I would just take 2 times 4, 2 times negative 2. You probably will do that in your head, and you'll get an 8, negative 4. It's actually really not all that complicated or tricky. So a couple examples. I do want to show this too on the coordinate plane because I'm going to ask you to do some problems like this. So it asks you to add these two vectors, for example, number 2. Vector 2, 3 plus vector negative 1, 6. Well, we're just going to do the vector math. We're going to add the x's, what looks like x coordinates. We're going to add the y coordinates. So I should have a 1, 9. So what I'm going to do when it asks me to sketch this graph, I'm going to sketch my first vector. All of these are in standard position. So always start from the origin and sketch it. Standard position, I can't walk and talk. So sketch them, and remember your origin is always your starting point, and then 2, 3. So that blue one is vector 2, 3. I'll even put that up there. 2, 3. I'm going to sketch vector negative 1, 6. So negative 1, 2, 3. So my standard position means my initial point is at the origin. This is vector negative 1, 6. Well, my answer when I add these two together might seem a bit crazy to you, but my final vector, my answer vector is 1, 9. So origin. So that is what my problem would look like for example number 2 when I do that vector addition. So sketch the two separate vectors as well as the answer. It doesn't make super logical mathematical sense when we add those two vectors, but we're actually looking at magnitudes and directions. So it does work if we go more in depth into vectors. I think we should be pretty good with this. Number 3, notice it's got a little extra. So I'm going to have vector 0, 4. And then I'm going to do that scalar multiplication, and I'm going to add that to vector negative 4, negative 6. When you go to sketch this one, you don't have to do the initial. Sketch just that second one when you've done the scalar multiplication. And then our answer vector for that one will end up being, if my math is right, negative 4, negative 2. And then we can sketch the vector 0, 4, the vector negative 4, negative 6, and the vector negative 4, negative 2. And I feel like everybody's probably pretty good on the scalar multiplication down here. If I triple my vector negative 4, 7, I'll have a negative 12, 21. Right? So it says to write the component form of the following vector AB, sketch the original and the standard form to check your answer. So let's do that really quick and then I'll stop talking, I promise. So notice it says vector AB. I probably should have written it as vector AB, but I know that A is my initial. I know that B is my end point. So I'm going to put those 2 points, and I don't like that I put these in brackets because those should actually be in ordered pairs, because point A is at 2, 3. Point B is at 4, negative 5. And when I make that a vector, I'm going to keep A as my end point, and I'm going to keep A as my initial point and make B my end point. So this is vector AB. So component form, I actually think it's easier to sketch it first because I like to count it. AB in component form, I'm going to take my B minus my A coordinates. So I'm going to do 4 minus 2, negative 5 minus 3. We'll see if this checks on the graph. 2, negative 8. So what that's telling me is to get from A to B, I'm going to go 2 in the x direction and negative 8 in the y direction. And it looks to me like if I'm looking at my calculations or at my drawing correctly, that looks like what I've got. If I put this into standard position, that means that my initial point should be on the origin. My end point should be at 2, negative 8, which it is. So that component form tells you exactly what your point, your vector will look like if you sketch it from the origin. And that is it for section 8.7. Write down any questions. Let's go back and retrack, retalk, see what we need to talk about, and we will go from there. Have a great day.